Thank you for the introduction and for the organization of the conference. So actually the title will be maybe slightly misleading because I intended my talk to be, rather general. And I'm mostly going to say a few general things on matrix models and their generalization to higher dimension, which is a random tensor model, which is the thing I've been spending the first year on my PhD on so far. And only in the later part of the talk will I mention new results we obtained regarding the double scaling limit of the quartic Owen model. So the main idea will be to show you how we can, through the simple use of combinatorial tools, we can deduce non-trivial results on scaling limits of tensor field theory. So random matrices have been introduced first by Wigner in the early 20th century to describe a heavy nuclei interaction, which was modeled by a random matrix. And now it has found a wide range of applications to various domains, mostly in data analysis or signal processing. But as you may have guessed, the properties that makes them relevant for my talk today is the use of random matrices to describe random discrete surfaces, which I will maybe sometimes refer to as simplical surfaces, which means like you can think of it as a triangulation, but using any type of a polygon. So random matrix theory is a zero-dimensional QFT, meaning that we don't have to work with a functional. The only measure we will have are simple probability measure. And so I'm taking a matrix M, which will be a emission of size n times n. And then I try to write the most general, the most general potential I could write. So essentially, it includes one kinetic term, which is a trace of m squared over 2. And then potential term, which have to be scalars invariants, so which are the trace, the higher order 10 trace of tk, the coupling constant, m to the power of k. And I choose the measure so that the Gaussian is normalized to 1. And then, as we usually do in field theory, I can work perturbatively, expand the potential, develop the series, commute the integral and the sum without being too wary of whether this converges or not, if I'm confident enough that I can get back information on the geometric series at the end of the day. And I can do my perturbative expansion in terms of matrix framing graph. So the matrix framing graphs are slightly different than the usual vector-like graphs because they have this ribbon-like structure. So on the left-hand side, you have the propagator. So it carries two strands, one for each index of the matrix. And the thing that matters ultimately will be that the two are distinct. And so on the right-hand side, you have an example of interacting term, which will account for the trace of M4. So you could imagine that each ribbon, each pair of edge is associated to one copy of the matrix, and then they have matching index in the corner, so that at the vertex I have a term trace of M4. And so like this, I can build my Feynman graph. So I simply put my vertices and glue them with the propagator. And then I can take the dual of this graph, which I have drawn here in red, and this gives me one simplical manifold, so built out of n gons that have glued together. So with this, you can interpret basically like each interacting term, m to the power k, will give you a k-gon, and then the propagator connects the edges of the polygon together and tells you like how to glue them together in order to form a surface. But actually, when we work with a random matrix, we do not work with the perturbative expansion. We work with the large n expansion, where n, so the size of the matrix, is n to infinity. And why is that interesting? Well, it's interesting because if you look at the shape of the potential I have, each vertex will come with a factor of n. Each propagator will come with a factor 1 over n because the propagator will be the inverse of the quadratic term. And then every time I have one face, so for example here in my graph, I will have a free index in my graph, so it will sum from I equals 1 to n and give me one additional factor n. So at the end of the day, the scaling of with n of any given graph is given by the Euler characteristic, which is fairly easy to compute. It's v minus e plus f. 2 minus 2g. This means that when I do a larger expansion, the leading order is given by the planar maps. Order 1 are maps that can be drawn on the torus, and so on. And so the matrix models are known. I mean, the one matrix models are well known and have been studied in a lot of different directions. So it's a mathematically very rich structure. Among others, it's exactly solvable, meaning that working under this larger expansion, I can compute any correlation function exactly. Also, they satisfy the Virasoro constraint, or also called sometimes loop equation. And using eigenvalue decomposition, it's possible to use orthogonal polynomial method, and this relates matrix model with some integrable systems. And all these three properties are hints that the matrix model can be studied using a more general framework, which is the framework of topological recursion. It's a framework that has initially been introduced to study matrix model, and now that has grown and extended to a lot of other structures, like array curves and this kind of thing. Just other things that matrix theory can do. So we can use them in intersection theory to compute intersection number. And also I can use it in string theory, as they can describe a knot invariant using, like, for example, Jones or Homfly polynomials. Okay, so now that you have a rough idea of how matrix theory works, how does it work with tensor? Well, mostly the same, except that obviously we have lost a few things by increasing the dimension. So first of all, there are many more invariants of order n. So here, for example, I have drawn the two quartic invariant that will appear later on. But so each black vertex represents one copy of the tensor with 3 indices. And then if two vertex are connected by an edge of color I, it means that they share a common is index. So for example, these two share the common first index, and so on. So yeah, there are already for the quart order 4, there are two different terms, but as it increases, there will be exponentially more. And so we can perform similarly a larger expansion, but it will no longer be a topological expansion, as for example, the leading order diagram will only contain a subset of what would be a planar manifold of dimension 3. And so as a byproduct, we don't have access to all the graphs in the 1/n expansion. We only know the leading order. So the model I want to talk about is the so-called Owen cube invariant tensor model that was introduced by Karuza and Tanasa in 2015. So I take a tensor phi with 3 index A, B, C, and I want it to be invariant under the action of 3 copies of the Owen group, where each copies act on 1 index. And so I can build 2 different invariants. So the first one, IT, which is called the tetrahedron, and the second one, which is called the pillow. So actually, these are the 2 distinct shapes, but for the pillow, I could draw 3 different pillows depending on the choice of color between these 2 vertex. That could be 1, 2, or 3. So I have 4 different interaction terms, but only 2 different structures. And so I can write an action for this theory like this. The scaling with n is chosen such that there is a non-trivial large n limit, and there is a well-known way to know which exponent to put where in order to obtain a non-trivial large n limit. And so the large n expansion is governed by the degree, which is essentially plays the same role as the genus before. So we have the number of tetrahedron and the number of pillow that increases the degree, and then it's decreased by the number of faces. Here, what I call faces are by analogy with the matrix case. So it means 1 loop for 1 given index. So for example, here on the left, you have 1 short faces of color 2, and so the propagator are represented as dash edge, and they carry the 3 index. So here, for example, I have a short loop of length 2. Or for example, here I have another loop of length 2, and I think that in this diagram, all the other loops all the other faces would be quite long. But yeah, the thing is they are defined by analogy with matrix model, but they no longer represent actual faces in the diagram. And so yeah, for example, this graph here would have degree 17.5. It's easy, if I give you a graph, it's easy to check its degree. So now the graph of leading order are called the melons. And if you look at the formula I had before and try to look for example with a few number of vertices, you will end up on one of these two cases. So either with the tetrahedron, you take two tetrahedrons and glue them together with a 3 common edge, or the pillow and you just create a loop under one of the sides of the pillow. And actually, you can see that if you were to insert this on any edge of a graph, it wouldn't change the degree. For example, for the type 1 melon, you can see that it has 2 tetrahedron vertex and 3 internal faces, and so NT compensates for F, and the degree is left unchanged. And the same goes for the pillow interaction. So this already tells you how to build a leading order graph in the 1/n expansion. You can just insert this structure recursively over and over. And actually, we are able to prove that these are the only way you can build a graph of a vanishing degree. And so this gives you a diagrammatic equation for the leading order. So now I can translate this diagrammatic equation into an actual equation, and I can plot the critical point for this function. And using the Lagrange inversion theorem, we have access to the behavior when approaching one of the critical points. And actually, for combinatorials, this is interpreted as a genetic function for trees. And so it will have a square root divergency. I mean, we expect it to have a square root divergency, which it has. So yeah, this gives me a way to, if you want, from a 2-point function to obtain new graph of the same degree by inserting this pattern. And now I can look to do similar things, but for the 4-point function. So the idea is the same. I take a simple graph that I had before, which was of leading order, and I try to look at the 4-point function I can obtain. And so this gives me a structure which we call a dipole, and we can compute the generating function for dipole depending on the generating function for melons. And the thing is, I can bring dipole together and insert it. When I have several dipoles, I can add or remove dipole so when I have several dipoles, I call that a chain. And in the chain, I can add or remove dipoles without changing the degree. So this gives me a second operation, which leaves the degree invariance. And so it allows me to repackage infinitely many diagrams which have the same degree when they will only differ by the length of their chain into a single object where I will have introduced the generating function for the corresponding chains. And actually here we already have a phenomenon that's more interesting than before, because now these chains introduce new critical point for the theory. Basically before, the only critical point I had was the one of M, and U was only a polynomial in M, so it had the same critical points. But now that I have U appearing in the denominators, then I'm going to have new critical points either for U equal 1 or for U equal 1/3, which will be relevant for the rest of the talk. And so now I define schemes. So schemes are just a way to repackage infinitely many graphs of the same degree together in one combinatorial structure. So how do I do that? Well, first I remove all the melonic 2-point subgraph, and then I replace all the chains I have in my graph by this box vertex. And that gives me the chain of a graph. And so I can study chain by, for example, looking at what happens when I remove a chain or things like this. And actually, by doing that, we can show that the set of schemes of a given degree is finite. So while at first there was infinitely many graphs of a given degree, when I write the contribution in terms of scheme, I only end up with finitely many of them. The downside is that as of now, I don't know how to obtain a whole scheme of a given degree. Like this proof does not give us an explicit recipe to build them. But however, when I look at the double scaling limits, I have additional information. So I forgot to talk about this. The double scaling limit for matrix model is a kind of continuum limit. So the idea is that if I want a continuum limit, I want to have as many polygons as possible. I want the number of polygons to use in my surface to go to infinity. But as I do that, and their size to go to 0. But as I do that, I'm gonna decrease the. And so as I do that, to take the size of the polygon to be finite, I have to take the size of the surface to be finite, I have to take the size of the polygon to go to 0. And so this corresponds to sending the coupling constant of the theory to a critical value. And now I want to do the same, but for schemes. But now, since I have several critical points that I can come at play, I have to look at which critical value can I reach from my theory from the origin. And actually, it turns out that this is the critical value that's relevant is the one for broken chains that came from the value u equal 1/3. So this tells me that in the double scaling limit, the diagram that will dominate this expansion will have a maximal number of broken chain. And so this is an additional information that I have on the scheme that contributes within this limit, and that will be sufficient to identify them. So actually, I know that in the double scaling limit, the dominant schemes all have this structure. So they are in bijection with trees, where like the root of the tree corresponds to the root of our diagram, so the two open edges of the two-point function. Edges of the tree will correspond to broken chain, leaves to tadpoles, and I will have these two types of internal nodes. So again, I have this combinatorial theorem that I can easily translate into an equation. So the 3t 1/2 is the contribution of the leaves. The 1 plus 6t is the contribution of the internal nodes. And the last fraction is the contribution of the edges. And since this doesn't depend on the shape of the tree, I can easily sum over the various trees that have 2 omega leaves. And I get, so this formula is simply factorizes as a Catalan number. And also I have an extra factor m accounting for possible melon insertion at the root. And now I can simply use the fact that we know how m behaves near a critical point to get this formula. And now I can look at this formula, and this tells me how I should define my double scaling parameter. So how should I send n to infinity and the critical value t and mu to criticality? So the idea is that the double scaling parameter is the quantity I'm going to hold fixed when taking n to infinity and t to its critical value. And it's defined in such a way that degrees of schemes of all degree omega will contribute in this limit. So basically, I have to make sure that that the last factor compensates the scaling in n, which leads to defining kappa of mu like this. And so now the generating function for dominant scheme of a given degree takes this nicer form. And now I am almost done because I can simply sum over the contribution of the various degree. And this just gives me a numerical factor and appears the generating function for the Catalan number, which is something that's very well known in combinatorics as well. And so we get this double-scaled two-point function, which turns out to be convergent for kappa mu smaller than 1/4, which is something that's to be contrasted with the result for matrix models where the series was divergent. So at the end of the day, I introduced scheme to repackage infinitely many graphs into a finite sum. And from combinatorial arguments, using this notion of scheme, we were able to introduce the dominant schemes that were contributing to the double scaling limit. And contrary to the matrix model, this double scale functions are convergent in a tensor model. And similar model can be applied to other models that are more general. So for example, multi-matrix model where we would distinguish one of the three index of the tensor to have a specific range in a 1D instead of being in a 1N like the other two. And that's all I had to say. Thank you for your attention. Yes. Okay, that's something I did not include in my slide. But basically, when you do this perturbative expansion, you expand around the origin. And so there's a competition between, so yeah, here you have the graph TMU. And so you have to look at which singularity you will encounter first when you play with your parameter. So if you run into this blue line first, or into which is a critical point for M, or if you run into a critical point for C or B. So the new critical point for C or B are the values such that U equals 1 or U equals 1/3. And actually, it turns out that U equals 1/3 is exactly the same as the blue line I have drawn here. And so if my diagrams have to be the most divergent, if you want, they're gonna have to have as many B's as possible. Because this is what will give me the diverging part of the diverging contribution. But yeah, I have skipped many details on that proof, so it's normal that everything was not clear.